Today we're going to be talking about simple harmonic motion, and the easiest way for me to explain this is through this pendulum system. So you're just going to have some bob or a mass hanging from a light string, and it's just going to be swinging back and forth. So let's say I start this bob from a height h, and we're going to say that it has an amplitude of minus 8 meters on this side and plus 8 meters on that side. So let's say we start this bob at a height h above the ground, or this bottom position, and at an amplitude of a meters away from the center. And what we're going to do is we're going to release it from rest. And this means that at the initial position, it will have maximum gravitational potential energy. And as it falls, this gravitational potential energy is going to get converted into kinetic energy until it reaches this central part where it's going to have maximum kinetic energy. And then as it starts to rise again, the kinetic energy is going to get converted back into gravitational potential energy. And at this point here, at height h on the opposite side, it will also have maximum gravitational potential energy. So let's look at how the GPE and the kinetic energy vary with distance from the center. When it's released from rest at this maximum amplitude A, it's going to have maximum GPE, which I'm going to denote in this green color. And as it falls to the center, the GPE decreases and then increases again at the negative maximum amplitude. Now, the kinetic energy is maximum at the center and zero at maximum amplitude. So you're going to get a graph that looks like this for kinetic energy. This is KE. So if we were to work out the total energy, which is basically kinetic energy plus gravitational potential energy, which is going to be the sum of these two graphs, you'll notice that you'll get a straight line. And this just shows that energy is conserved in this system, which makes sense. If there was no air resistance, this pendulum would just keep swinging forever. Now, for this pendulum to move from its maximum position to the central position, it would take a time of 1/4 of a full time period. In fact, each of these little sections here all take a quarter of a full time period. So as it moves from maximum height to the central position, or vice versa, it will take a quarter of the time period to do so. Now, there are a couple of equations that you need to know for working out the time period for different systems. You do not need to know the derivations of these equations for A level. So for a pendulum, the time period is equal to 2 pi times root L over G, where L is the length of the pendulum. So that will probably be the length of the string or the rod that you're using. And G is gravity. If it was on Earth, G would have a value of 9.81. You also need to know the equation for the time period for a mass spring system, and this is where you have a mass connected to a spring and it's just vertically oscillating up and down. The time period here would be equal to 2 pi times root m over k, where m is the mass you add onto the spring and k is your spring constant. So now let's look at the displacement, velocity, and acceleration versus time graphs for simple harmonic motion. For the pendulum, the displacement is going to be the distance from the center. So the maximum displacement of this pendulum is going to be A. And if you were to draw the graph based on what you see, you would notice that if you released it from the start at point A, after a quarter time period, it goes to 0. After another quarter time period, it goes to negative A, and it repeats the same thing for a full time period there. And this graph here is a cos graph. So the equation for x in terms of t is going to be x is equal to a cos omega t, where omega is equal to 2 pi over t. And remember that from our previous video on angular velocity. Now, to find the linear velocity versus time profile for this graph, remember that working out the velocity from a displacement time graph means that you need to calculate the gradient. And in this case, in order to obtain the velocity equation, you need to differentiate the displacement equation. So the velocity is going to be equal to dx by dt. And remember that x was a cos omega t. So if you differentiate that, you would get minus a omega sine omega t, because cos differentiates to minus sine. So the graph you will see will look something like this. Remember that in this case we are releasing the pendulum from rest at the start. That is the initial condition in order to get this graph. And you can see that at a time period of t over 4 and 3t over 4, you're going to get maximum speed. And the value of this maximum speed is going to be minus a omega or plus a omega. Now to work out the acceleration, you do the same thing you did for the velocity, but with the velocity time graph now. So you're just going to differentiate the velocity equation. So acceleration is equal to dv by dt, which if you performed it, you'd get minus a omega squared cos omega t. If you are unfamiliar with this, you will go over this in your A-level maths course. So therefore, the graph of acceleration versus time will look something like this. You will notice that this graph looks like the reflection of a displacement graph, and that is actually what the definition of simple harmonic motion is. Definition of simple harmonic motion is when the displacement is directly proportional to the acceleration, but in the opposite direction. So the acceleration will be directly proportional to the negative of the displacement. And you can convert this into an equal sign by adding a constant. And in this case, for all simple harmonic equations, the constant would be minus omega squared x. And in this case, omega is exactly what it always is, which is 2 pi over t. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.